Yes, and dear participants, welcome again. Today, we talk about the satellite geodesy and its applications with Professor Dr. Mehdi Esak. Before giving the words to Professor Mehdi Esak, I would like to introduce a brief introduce to him, and his master uh, degree from and PhD degree from physical and space geodesy from the Royal Institute of Technology, Sweden, and he has been working as a professor of geodesy since 2030 at University West from Sweden, and he has the 20 years experience, teaching experience, and I know him, know very well-known paper and the meetings and the conference. And I asked him this online meeting to participate, and uh, my special thanks go to Professor Mehdi to accept this invitation. And I think that I give the word Professor Mehdi. Welcome.
Thank you very much, Dr. Samed. I'm really grateful that I have this opportunity to talk to you and other guys at University of Samarkand in Uzbekistan. That's what I'm really honored for that. Thank you very much for inviting me and
Sorry,
organizing.
excuse me.
Yes.
Excuse me. Please, oh, dear participant, please close your microphone and the camera. And because the system causes the system affect these uh, overloading. Please close your microphone and camera. Yeah, but please, Dr. Matt, please go on.
Okay. So before I start, I want to make sure that you see my screen. Do you see my screen?
Yes.
The presentation?
Yes, we can see.
Yes, I'm going to talk about satellite geodesy and its applications, but I would say that not all applications. That's the applications that I have done, actually, the things that I have done, my journey in satellite geodesy. That's what I'm going to talk about. So probably you will find more in lecture and literatures and also in papers, but what I'm going to present is what I have done. What did you? So, satellite geodesy is my former and current subjects, and the things that I present is also the research that I have done so far, and also the things that I am doing and I will do in the future. So let me, before I explain what is geodesy, and after that, I say how satellite geodesy grow or appears out of it. The science and technique of determining the Earth geometric shape, orientation, speed, and the gravity field is called geodesy. So it means that we are measuring the Earth. We have geometric eyes. For example, I can say in geophysics, we study the physical properties of the Earth. In geology, we try to understand the physical properties, not to model, but geophysics is modeling. But in geodesy, we just look at the shape and this form. And it also changes in time, of course, the gravity field. But satellite geodesy comes when we use artificial satellites for such a purpose. The good thing with satellites is that they are far from the Earth and they can cover large areas. That's the importance of satellites. And we can have satellites like a good, if you have, for example, some instrument that they are measuring, that they measure the data in a uniform quality. That's very important. And unlike the terrestrial measurements that which are very much dependent on the high frequency nature of the field, gravity field, or also other type of things. But when we look at the satellite, we look at the Earth in a general sense, in a global sense. Satellite geodesy normally is divided into two pieces. The first one is geometric satellite geodesy. That then we just look at the geometric properties of the Earth. Satellites are targets. What does it mean when we say it's target? Target means that they are noun points. They have coordinates. And we try to use their coordinate to determine the coordinates of many points or any points at the Earth's surface. That means target. But in gravimetric satellite geodesy, the goal is to study physical properties of the Earth and its gravity field. And in this case, satellites are sensors. Here, the position of the satellites are determined, but they are not target for coordinate transformation. We measure the satellite to check and see how they vary around their orbit around the Earth. That's the main goal of the gravimetric satellite. If I say that satellites are target, the main important thing is that to see how these targets have the coordinates. Actually, we have some networks of points that we have already determined the coordinates of these points, but other space techniques like VLBI or SLR or other systems. And then these coordinates from this terrestrial terrestrial stations are injected to the satellite, and the satellite gets the coordinate. It means that the satellite itself is just an instrument. They do not have a coordinate. These coordinates are computed by the terrestrial or the ground stations, and they inject it to the satellites, and they get the coordinates. And thereafter, the satellites transfer the coordinate back to the user. So this is what do you do in the GNSS measurement? And you apply, for example, RTK, positioning, navigation with your mobile. What is happening is that some people, they are working on stations, ground station all over the globe, compute the orbit of the satellites, compute the coordinates. They send it up to the satellite, and the satellites are transferred them back to the Earth. And you get that coordinate from them. So in that case, more measurements are normally we call code, phase, Doppler. There are different types of measurement. And the main goal is to transfer the coordinate from satellite to the user segments or users around the world. When satellite is sensor, as we know, the Earth's mass is not homogeneous. Some parts of the Earth are heavier than the other. We have mountains. We have also water, lakes, and this is that the Earth is not actually homogeneous. And when the satellites move around this Earth, the orbit is not completely an ellipse, as Kepler said. There are some perturbations around the orbital ellipse. In that case, our goal is to determine these perturbations. And by looking at how much a satellite will be perturbed, comparing with the case that the Earth is homogeneous, then we can determine the gravity field of the Earth. In that case, the satellites are closer to the Earth's surface to measure it better. GNSS system.
Could you please close your microphone and camera, please?
So let us move on. Satellite geodesy purposes. Well, again, on the left, you will see that this the left you see the application of geometric satellite geodesy is normally are classified in GNSS, GPS, GLONASS, Galileo, Magdo, EGNOS, and other systems. These type of systems can be categorized as geometric satellite geodesy systems. The purpose is to determine coordinate, absolute coordinate, relative coordinate, kinematic coordinates for different navigation, deformation monitoring, measuring the changes of the Earth's surface and so on. Modeling ionosphere, troposphere, and also radio occultation is for tropospheric modeling, sea level variations, determination of the soil moisture, and modeling of ionosphere over ocean. So these are the challenging things that they are now working today for GNSS reflectometry. So I will talk about it later. For a gravimetric satellite geodesy, we have a different perspective. So there have been some what's it called? Near Earth surface satellites like CHAM, Challenging Mini Satellite, Payload, GOAT or GOES, GRACE, and GRACE. These are the satellites that are designed to determine the Earth's gravity field and its temporal changes. The problems like orbit integration and prediction, which is also done for the GNSS satellites, is a part of gravimetric satellite geodesy. You need to have the gravity field of the Earth to predict and compute the orbit. You can also determine the gravity field globally, locally from this type of satellite missions. You can model crustal structure, sublithospheric and lithospheric stress, eventual viscosity, and post-glacial rebound, determination of groundwater storage, squid monitoring, and ocean bathymetry, sediment basement determination. These are the subjects that I just mentioned, some of them here for the application of gravimetric satellite geodesy. What type of measurements do we have for this? As I said before, for geometric satellite geodesy or GNSS, we have some measurements between the satellites, which are noun point as a target, and also the unknown, which is receiver. So code measurements, carrier phase measurement means that the satellite send the signal down to the receivers, and at the same time they send time and their coordinates. So this signal which goes, this is called carrier phase. This is a signal which carries the coordinate. Range rate, the changes of the range between the, for example, if we have kinematic applications, the satellites, and also the, for example, the car moving, and this range changes. The range rate can also be used for that Doppler shift, and also laser ranging could be a part of this. But for gravimetric satellite geodesy, the measurements are actually the orbit itself. We determine the orbit of the satellite to investigate how the satellite moves around the Earth. Based on the perturbed motion of the satellite, we can determine the gravity field. Then for position of the satellite, velocity of the satellite, acceleration also can be used for gravity modeling. The second order derivative of the gravity, which is called gravity gradient, is also can be used for determining also intersatellite range and radiance, which I will explain a little bit deeper later. For satellite orbit, what is happening in satellite orbit? So the issue is that, let me show it with a pointer. So we get coordinates from for example, a low Earth orbiter like this is a CHAMP satellite actually, and we have GNSS satellite above them, and they determine with the same technique that we use for example, coordinate determination with GNSS. We determine the coordinates of this satellite. At the same time, we measure from the cellular or laser data with the retroreflectors, which is under the satellite. We can measure the coordinates of the satellite. So, and based on these coordinates, we can determine the movement. How can we determine the movement? Based on three methods. Dynamic method, when I use the force models, I can determine the orbit. I can use kinematic methods. This is a kinematic method is that I combine the satellite data that I have collected from GPS, for example, or SLR data. They have an orbit for that. I don't care about the force models or gravity field. I determine the coordinate directly from satellites. That's called kinematic, and semi-kinematic is combination of them. So generally, for a satellite, a satellite will be affected by non-gravitational forces and gravitational force or perturbation. Gravitational forces, gravity field, for example, solar. I would say the solar and lunar tide. Yes, the tide, but the Earth body moves every day up and down 15 centimeters based on the tide. Ocean tide, we have the gravitational attraction of other planets, also general relativity, and also many other things. Non-gravitational, mainly important for low Earth satellites, air drag, which nowadays with some instruments, they can measure this. Measure the drag-free systems. Actually, the satellite movement are not very much influenced by air drag, but there are forces like that. There are forces for radiation pressure from the satellite, radiation or reflection from the satellite, from the Earth surface, also thermal effect. The satellite gets warm and they will emit signals. Then these are all important for us. So, based on all these things, how can we come to gravity field? So if I know these gravitational perturbations, which we know, and also non-gravitational perturbation were on the side, and I measure the orbit, and I subtract this gravitational perturbation and non-gravitational perturbation, what remains is an orbit which is influenced by only gravity field. In that case, then you have to find mathematical models to invert the orbit back to the gravity. How it is done is a long process. I'm not going to talk about it. But the problem of orbit determination with the dynamic method, for example, is the opposite to the local gravity field determination. Here, from gravity to orbit, you will add these perturbations to counter the orbit. When you have the orbit and you want to do gravity, you need to remove these gravitational forces. This was the, let me active this pointer. I started this subject around 20 years ago. Of course, I started this in 2000 about orbit determination, and when I did my master thesis. On that time, the CHAMP mission was a hot subject actually, and the orbit determination was very much popular at that time. So that it was, I started actually this dynamic satellite geodesy fund. Another type of measurement which is used in the GOES mission, which is gravity field, steady state, ocean circulation exploration. I emphasize steady state. It means that the goal is to determine the static gravity field, not the changes in time. So I have the gradiometer, and it is like we have two accelerometers. So in the along track direction, cross track direction, and radial track directions. And these two accelerometers measure the acceleration distance is around 2 meters, I think. So when you have the measured acceleration, the difference between the measured acceleration will be the gradient or the second order derivative of the potential. That's all. Why is it important? Because by using the second order derivative, you can recover higher frequencies or more details of the gravity field than the orbit alone. So orbit alone doesn't work actually. You cannot go to high frequencies of the gravity field, even if you are close to the Earth's surface. But if you use the gradiometric gradient, it means actually taking the derivative. If you are good in mathematics, you understand that taking derivative means taking derivative is an amplification. When you take derivative, you amplify the differences in the frequencies. So that's why we have the chance to get higher high resolution gravity fields, but in a static, well, I'm saying static means that it's just one model during the satellite mission. GOES was designed for 2 years, but it worked 3 years, and that we were lucky. He gave us much more information that we expected, so that's really good in that. And the goal is that to analyze all the 3 years data of this mission to determine the one gravity mover. That's called static. This is always steady state. So this was the subject that I did when I was PhD student. In 2009, I did my PhD on satellite gravity gradiometry in this subject, and my goal was to determine the gravity field locally from the satellite. So that was the So the problem that I had to solve was that because there are atmospheric masses, topographic masses under the satellites that which are not actually wanted. We wanted, and then I have to compute these things and remove them from satellites, from the measurements or gradients, and later continue the satellite downward because the measurements are at deep 250 kilometers above the Earth's surface. But what I needed was down. When I want to draw that down, bring them down, the noises of the data will be amplified by that. And I had to find a way for controlling that noise. Then determining local gravity field determination and validation and outward continuation was like that I have the gravity data here at the surface of the Earth. And with some methods, I try to regenerate the gravity gradients from the test area data. So that was in order to validate if this data are, the quality of this data are good or not. That's what. These are what I have done this, and later I submitted another report for getting a docent title at KTH for physical geodesy and space geodesy, but I completed actually this type of studies, my studies actually in gradiometry to get that title. And later I published a book about the satellite gravity gradiometry. It is actually the revised version of my PhD thesis that I published there. But the story of a GRACE is different because GRACE is not one satellite. GRACE is designed for measuring temporal changes of gravity. So, for example, we have, as you see, climate experiment. Climate is not constant, and it's changing entire gravity field and climate experiment. So GRACE and GRACE follow on because we have had GRACE for 15 years, and after powers of 2 years, another GRACE mission came, and we can call it GRACE 4 or GRACE follow on. But the principle is the same. So two satellites following each other in one orbit, and they measure the distance. They measure the distance between them precisely, and also they get positions, or they are positioned actually by the GNSS satellites, and also some SLR data from this. So the position of these satellites are determined precisely. At the same time, the distance between satellites is measured. This is what I'm going to talk about actually more, the distance between satellites. So the goal one goal was this about changes of the gravity field and modeling the groundwater storage. We are in a water crisis these days, actually, and the way to monitor how water moves on the ground can be done by GRACE. And also we can study earthquakes and post-seismic activities by the GRACE mission, because if you can have gravity field before earthquake, after the earthquake, some changes will happen inside the mass of the earth, and definitely the gravity will change, and you need precise measurement of the gravity. So around I was for doing some studies about GRACE. I was in the French Space Agency. I don't remember, more than 10 years ago. I don't remember which year. And we studied this subject, actually. We wanted to see how much with mathematics we can fix these misalignments between the satellites. So that was the idea, the things that we did and worked on that. So another totally different application is to study lithosphere. The first thing, which is actually known in geophysics, is the MOHO, or MOHO density concept. MOHO is the abbreviation, actually. It's the first part of the name of Mohorovic, Andrei Mohorovic, who defined actually this surface. What is this surface? If we have crust floating on the surface of the viscous mantle, and the shape of this the boundary between the crust and mantle is called MOHO. For determining MOHO, there are different methods, actually. One is the seismic data. We put the seismometers and put them on over at the surface of the earth. They sense signals and get it back. Then, because the density will change, as the density of mantle is higher, much higher than density of the crust, not much higher, but higher. And then it's reflected, they can measure the depth of MOHO from the surface of the earth. So that's one way. But the other way is to use the gravity, or some hypothesis which is called isostasy. In isostasy, the idea is that, it's not the idea, the assumption is that the crust or the mountains have the roots beneath. That was the idea. The story is related to a long time ago when the Everest, it was a military man, wanted to determine the map of India, and he made a geodetic network over that, and he realized that the deflection of vertical around that area is not as it should be. Then he realized that, okay, the mountain should have a root so that this deflections comes in the right direction. So this is what actually he found this. The later IRI started to model actually this issue, this theory, and he assumes that the Earth's crust is like columns, and the one which is longer or taller or bigger penetrate the mantle more, goes inside mantle more. So the mountains have roots. Also, there is another assumption or hypothesis that Brad says that, okay, they go to the same level, all of these plates, because the density between the columns are different. But in IRI model, they have the same densities. All column height at the same density, but in Pratt, no. And later, very many minus came into that you cannot consider the crust at all as columns, separate columns, because there is shear stress between the columns like that. You cannot ignore that. This is why he said, okay, this compensation means that to compensate the weight of the, it should be more of a regional than local. So that was the story of the MOHO, and that's this MOHO and the isostasy, and the boundary that Cross has on the or roots of the mountain is called MOHO. And we will use actually MOHO and density contrast, which is the density difference between the cross and matter, for other things that I have explained here. We continue. So density contrast is the thing that we could also determine by satellite data. And here you see this density contrast that we have determined for Central Asia, Asia or East Asia, or over Asia, Eurasia. And then you see that the density, the MOHO you see on the left-hand side, and the density contrast you will see on the side. Just so that these places that you will see, they are red, very red. That means that the contrast is high, and the RS contrast, the blue is contrast is low. And here you see the left side, you will see the MOHO, and the red one is the deep MOHO, and the yellow and other one is the blue one are not deep enough. And here in that study, we use gauge gravity gradients. Actually, so we have used satellite data for determining this. So I have had a collaboration with University of Geodesy, Pakistan, and it was Matlub, Dr. Matlub. He did his PhD with me here, and his goal was to determine the MOHO density contrast, and also stress in the pipe. So in this study, you will see that we have determined the MOHO of the over in the pipe plate from the ghost data, but here you use unorbit ghost data. We had to combine them with some other terrestrial data and some seismic models like Crossbond. And we come to this value of MOHO depth. Later, we estimated also the stress under the same area in the pipe plate, but again using the satellite data. So as you see, the stress comes to around 90 megapascal over this area, and this has very good correlation with the seismic points that you will observe here actually as red points. So then we did it actually in a collaboration with Professor Kirsti Tiempo from University of Boulder, I think, USA. So she helped us with interpretation of the geological interpretation of this. And later, we did some studies about the gravity gradients, the changes over the earthquake, actually. Kashmir earthquake in 2005. As you see, we have considered the second vertical gradients. It means that the gradients to measure vertically, horizontal gradient, horizontal vertical like this, and horizontal gradient. And you see here, let me show you the pointer. And the left-hand side here of this vertical gradient, and you see that there are a huge value of the gravity field before the earthquake. Earthquake happens around this area, as you see. There's a tectonic border actually passing through Pakistan. And you see that 2 months before the earthquake, we have had the huge value here of the huge anomaly, I would say. And it's getting closer, and after the earthquake, it goes away. The same pattern almost is seen of the other gradients, but the vertical gradient was very visible. Of course, we had to be careful to remove the effect of hydrological signals, because the main mission of GRACE was to monitor water movements. So if we want to study the gravity changes, actually, we have to remove the gravitational effect of the water moving from hydrological models. So that's what we have. Now, Dr. Matlub is now associate professor at the same university, and I'm very proud of him. Another thing that we can study with satellite data is mantle convection. This is very interesting because convection happens inside the air, very deep, and satellites are outside, far from this. How can this be connected? So mantle convection, also tectonic movement, as you know that this mantle convection has direct relation with tectonic movement. So geometrically we can measure, put some instruments, permanent stations over continents, and measure the changes by GPS and GNSS simply to see the direction. And there are models for that, and you have seen that. But for the mantle stress, for example, what can we do with that? Here I will present one of my works actually that I collaborated with Bernard from GFZ from Germany, Robert from Hong Kong, and Anders Tassara from South America. We did a study for modeling this the gravity, but using satellite. I have used ghost data in that study, and Bernard Stamberger tried to actually not tried. He estimated the stresses based on another way, not from satellite, from seismic data and the deformation or the plate tectonism. And I tried to use them and combine them with satellite data. When we get the data from GOES, and we will invert them in such a way that they are constrained to the seismic data. In that case, we come to this result, and which is actually true and correct. We know that the Nazca plate is pushing the South American plate, and you see that all vectors here, let me show all vectors pushing to this South American plate to the east, and what is expected to see actually. Also, there was another study actually we did for an earthquake in Iran, and it was Grace 4 this time. And the issue was that this earthquake happens inside the crust. Actually, we say that how deep is the earthquake? Based on the seismic data, we found that. And later, we estimated how much changes in gravity will happen, and that we transfer the stress from bottom of the lithosphere or sublithosphere to the point that the earthquake has happened. It's not sublithospheric, it is something inside lithosphere. This stress propagation has its own problems, and we say that if the gravity field or equipotential surfaces can change in time, then we can estimate them. They are like surfaces. So then we can estimate it's a displacement field, and from the displacement field we can determine the stress and strain. So what you see on the right hand side actually is that this is the strain map actually, and this is strain map. See that here, as you see, it is a point that the earthquake has happened. There's a hop square here, and you see the stress around it, and it is here. You see the other the elements of the strain transfers, and you will see that it's here something that shows us some shear strain has happened around that point, which make this earthquake strong. So let's move on. Elastic thickness, as you see, if we can consider that it's a lithosphere and we have a load from it. And based on this load, is lithosphere or this shell or lithosphere shell is bent downward. So the thicker this lithosphere is, the bending will be less clear. So based on this problem, based on this issue, I assume that okay, if the gravimetric moho is equal to flexural moho, if it is lithosphere and it is bent like that, And also based on the gravimetric data, I can determine this MOHO as well. But the difference is that in the flexural isostasy, I use the physical properties of lithosphere, but in gravimetric MOHO, I use the gravimetric data, density, the boundaries, the shape, and so on. But in flexural, I need, for example, Young modulus, force ratio, and elastic thickness. So if I say that, okay, if I consider that the gravimetric MOHO is equal to flexural MOHO, then I could come with a method to determine elastic thickness for combination of these two. This is what I have done actually in 2018, and I presented a theory for that and in a spherical harmonic domain, and after that I applied it for South America. On that time, Martin Pitunak was with me for a sabbatical, and I asked him to develop this a little bit further to ghost data, satellite data. And what you get here for South Africa is a result of our investigation and calculations. And you will see that the elastic thickness over these red areas are too large and the rest on the beam. So this is what we have done based on satellite data again, ghosted satellite gravimetric data, which cannot be done with any other satellite methods. It should be satellite gravimetric data. So later, about post-glacial rebound, I say that the GRACE measures the changes of the gravity field, and the changes of gravity field, post-glacial rebound is one of the geodynamic phenomena. What is it? It says that if we have a load on the lithosphere, and lithosphere on the mantle is a viscose, what will happen if the load is gone? The lithosphere is going back upward. So in that case, I try to use the post-glacial of the lithosphere to see, and right now I used GRACE data actually for measuring this, and we determine the changes of the gravity, the changes of the geoid, and later I could, with some theories that I have, we change it to the height. This is what I have computed for the Fennoscandia. As we know, that a long time ago, about 20,000 years ago, there was a big ice cap over this area. And this big ice cap pushed the lithosphere down to the mantle. And now the ice cap is gone, and the Earth, or the Earth's lithosphere, is under the permanent post-glacial rebound, or glacial isostatic adjustment is going upward to come back to this equilibrium. So that's the way that during the 15 years of the measurements of the GRACE, I determine this geoid changes, and from the geoid changes, I come to the changes in the land, actually height. And as you see here, it's around 8 millimeters per year. We have here, the central part is around the city of Umeå. Yeah. And here's what I have done. I have checked it with the terrestrial GPS data, and they are really consistent, so no problem. And the next thing that we can determine from GRACE and GRACE-4 data is the groundwater variation. What we get from the GRACE as actually is the changes of the gravity field, or changes of the potential of the field. This potential is the result of many things, these changes. So what are these changes? The changes can be from the groundwater, they can be from soil moisture, they can be from canopy, they can be with snow, and all these things together are create the changes. But what can we do? GRACE give this gravity variation. We can change it to equivalent water height. And later, if we subtract soil moisture, canopy, and the other snow water equivalent from the GRACE data, we can come to the groundwater. That's all. Very simple. And as you see here, the map that we have created with the help of Farsam. And we have seen that how the groundwater is changing, but it's in global level, it's not regional. But I should say that the post-glacial rebound over these two areas in Hudson Bay in Canada and also Finland have not been taken into account in this map. So you will see how much we have water here, as you see here, and how much lack of water do we have over the black area. So for example, Greenland, as you see here, the left side, we have lack of water during this. And here, it is also negative here, for example, around this Tanzania here, India, and yeah, and also Iran. These are the negative values that you see here. So with satellite gravimetric data, we can also determine the groundwater variation. So I wrote a book in 2020. Of course, it took 2 years for me to write it, and I have explained all the theories about gravity determination, about bathymetry, sediment thickness, ice thickness determination, everything inside that book. Then if you're interested, you can have a look. Now, some collaborations with Ethiopian Space Science Institute, and why Ethiopia is important for me. Of course, it is important for everybody, I would say. But because there is a mantle plume on the Afar area. What does it make different? What is the difference? I said that isostasy, we always say that these mountains, they have roots. It means that if we have mountains, then we have some deep, but in reality, over this area, this is not true because there are other things which keeps the mountains up. And one of them is mantle plume over this area. So the theory of isostasy actually is not very valid here. So in this, for this, I have on the net Ashagriya, who Dr. Ashagriya was my PhD student, and he has done some investigation for determining moho and elastic thickness here. Is Dr. Andernet around?
Yeah.
Dr. Andernet, please take the wheel.
Can you share the screen for me because it is not visible for me? The screen. Hello?
You don't see this?
Yeah.
Don't you see this?
No, I just hear your voice.
Let me see.
Because of technical problem, I rejoin again. That's why maybe.
Okay, let me come back. Is Dr. Samad around?
Yes, I am here.
Do you see my screen?
Yes, but now I didn't see. It's I think you remove your presentation.
When?
When 1 minute ago.
Okay. So you scared me. So you see. No, yeah. Let me see. Keep you on. No, Scott. I will share again. Then.
Mm-hmm. Yes, we see.
So let's see if Dr. Andernet can come.
Yeah, I'm not looking at it. I don't know why. Can I speak only, maybe, without looking at it?
Yes, you can.
Okay. Hello, everyone. My name is Anjanat. I did my PhD with Professor Mahdi since from 2017 to 2021. What we try to do in this study was isostasy in our region in Ethiopia. Due to Afar mantle plume, the area is not in a complete isostatic equilibrium. So we try to add this effect in the competition of MOHO, as well as effective elastic thickness of the lithosphere and stress inside the lithosphere. What we did was we take the mantle plume model according to Morgan in 1995, and which is also adapted by Morgan in 2015, and we compute the vertical stress due to mantle plume around the Ethiopian hotspot region, and include this effect in the MOHO competition, because in the case of MOHO, competition, as the professor already said, we include different mantle heterogeneity effects, such as the sediment, crystalline, and we also include the topographic barometric effect, and subtract this effect on gravity disturbance, which we recover from Gauss gravity, and computing the MOHO based on this cannot give us good results because of this effect, mantle plume effect, and the region is not in isostatic equilibrium. So what we did was include this effect from mantle plume model developed by Morgan inside this many Morse's theory of isostasy, and not only with MOHO, we include also this effect in the effective elastic thickness of the lithosphere. As you know, as it's already said, these effects are estimated by combining the gravimetric isostasy theory and the flexural isostatic theory. And in both these two effects, we include the mantle plume effect as a load in the flexural isostasy, and as also gravity disturbance in the case of gravimetric isostasy, and computes the effective elastic thickness over the study area of Ethiopia, and the result was gives a significant improvement when we compared it with previous studies, because maybe if you look the picture, the one on the left and the right, the effective elastic thickness over the Afar region should be smaller from the previous studies, but when we don't include this dynamic effect, it gives us a very large value, and when this dynamic effect is included and estimated the effective elastic thickness of the lithosphere, we found significant improvement in the solution when we compare it with other similar studies, which is done by other method like spectral method. So we did also the same for stress estimation inside the lithosphere. In this case, we take, in the normal case, we take the horizontal shear stress due to mantle convection as a boundary value to estimate the stress inside the lithosphere. But in addition to that, we include in our study the vertical stress due to mantle plume. And the study also shows when it is compared to World Stress Map 2016, the maximum shear stress direction given by this World Stress Map 2016, and the stress we compute when we include the mantle plume effect has a higher correlation than without considering this dynamic effect. So this is our result. Maybe I finished it. Thank you.
Okay, thank you very much, Dr. Andanet, for that. And let's move on. So also we have some studies about cluster deformation and stress using the INSAR data and GNSS. And this is Andanet Negusiye who is working with that. Andanet, are you there?
Yes, yes, Professor.
Andanet, please explain a little bit about what you have done about this study.
Okay, thank you for the chance.
Yes, please.
I am Andanet Nuguse from Ethiopia. My institute is Ethiopian Space Science and Technology. I am a PhD student there. And I am working my PhD on the title Estimating Three-Dimensional Displacement Around Afar Area by a combination of GNSS and INSAR data. And as you can see from the picture, we have selected Afar area because Afar is one of the most sensitive areas. That means Afar is one of the area where there is active volcano. And as you can see, there are 7 GPS stations. The GPS stations are in green, as you can see. And we took the data of this GPS station and processed with Gamit Globe K software, and we arrived with 3-dimensional displacement for each GPS stations. And why we choose this area? Because it's active volcanic areas. And then after we process this one, we have also used we have also used INSAR data. We do use Invisat ASAR satellite to take the data. And we have, as you can see, the ascending and descending track. When you say ascending, the satellite, when the satellite moves from south to north, the descending is from north to south. And the left-hand side, as you can see, is the result which is obtained by processing the data using SARPROS software, and the red line shows the area where the land is moving away from the satellite, and the green shows the area where the area where it's moving towards the satellites. Okay, so here in the red area, we do have almost maximum 10 millimeter per year displacement, maximum 100 millimeter per year displacement is observed there. And we do have now, this is of course the line of sight displacement result. One thing what you have to understand is that the GPS satellite will give us 3-dimensional displacement, whereas the INSAR satellite will give us only line of sight displacement. So we have to find the combination of the two GPS and as well as the INSAR satellite in order to determine 3-dimensional displacement of the area. And as you can see from this figure, this is a combination result of each GPS station. We have selected, as I have said, 7 GPS stations, and the result of the displacement, that means displacement rate is shown for each GPS station. I think it's visible in the picture. So we have now 3-dimensional displacement, the combined 3-dimensional displacement from INSAR and GPS. By the way, in order to combine this INSAR and GPS result, we do use Markov model. We do use Markov model, and after that we have arrived this result. And the next work what we are going to do is what we will do is that estimating stress and strain of the study area using finite element method. Finite element method, we are going to estimate the stress as well as the strain of the study area. This is our work. Thank you, Professor.
Thank you very much, Andanet. Let's move on to the next slide. So I present another work that was with Amin. Amin Alizadeh was one of my PhD students, and of course I didn't complete his PhD. Half of that it was with me. And here we try to use a optimize GNSS network over a very sensitive area in the western part of Sweden, which are there are many clays there. So it's a high risk of landslide. So they have had a network of points there, as you see on the left, and we try to optimize them. If we want to come to the same accuracy, can we use less observations, less measurements? Why should we use too many measurements when we can come the same thing with it? That was the idea. We have to try to optimize this landslide GPS monitoring network over this area. As you see on the left, this is the original GPS network over that area, and the green one here you see is the optimized one. And the third one is that those observations which are not necessary, which are not needed for that, then we could come to the same result with the same quality, and without this. That was one thing that Amin was working on that, and later we continued this studies later further for optimization of the deformation monitoring network using finite element. This was really different than the other optimizations that has been done so far. That was for the Skåne area. As you see the area in the map, the down here is Skåne, and you see the GPS point, and they have designed networks for that. And the idea here is that we needed to have a mathematical model for minimizing the stress error, strain error, not the precision of the precision and reliability or other factors are some constant we put it. But what we were going to minimize actually here was the strain error, because the main issue for deformation monitoring network is the strain, not the precision of the point. How much changes how sensitive this network is with respect to the changes. And here you see that the networks, this is the Delaunay triangulation, and after that, based on the Delaunay triangulation, the strains estimated, and those unnecessary observations have been removed, actually. But here you will see that different type of optimizations and some of the constraints that have been applied for optimization, etc. So this was what Amin has done it, but unfortunately Amin could not come today to explain further this issue. Then let us move on. So we have future works focus that I have now actually in my study is that multi-GNSS application. So we have many and now GNSS satellites around the Earth now, and it's better to use all of them for getting high precision. So another is precise navigation, modeling ionospheric, troposphere, and GNSS reflectometry and radio occultations that we will explain it later. So the problem of positioning that's rather known actually is I have some collaboration with Kansas University for this. And then for positioning, it's clear that the signal passes through the atmosphere and ionosphere and troposphere, and is reflected. So, and then there are methods for handling these things so that we get the coordinates not affected that much by distance, because we can measure, we can minimize the disturbance that comes. So we can determine the coordinate. Now, assume that you have the coordinate, and now this time the goal is to model ionosphere or troposphere using this satellite measurement, using this distorted signal. Actually, that is what is called GNSS meteorology. So that's what is called what is done actually. That I have invited a colleague from Kent University. Is Hani there? Hani Mahboubi?
Yes.
So
Thanks, Professor. Thanks, Professor.
let me share the screen. Do you see the screen, Hani?
Yes. Yes. No.
Yes, please. Go on.
Thanks, Professor. Hello, everyone. I want to speak a few words here about satellite geodesy and ionosphere. One of the applications of satellite geodesy is retrieval of the atmospheric.
Excuse me. Excuse me. There's an interesting voice here. And please, dear participant, please close your microphone. Please. Please go on, please. Yeah, Honey,
Yes.
if it is okay for you, you can go on.
Thanks. One of the applications of satellite geodesy is retrieval of the atmospheric parameters using the satellite receiver pair observations. Ionosphere is the upper region of the Earth's atmosphere that has ion and electron concentration. This region starts from an altitude of about 60 kilometers, and there are electrons up to about 1,000 kilometers. A significant portion of the electrons are concentrated at altitudes of 150 kilometers up to 500 kilometers in thermosphere. Next slide, please, Doctor.
Sure. Do you see the next slide?
Yes, thanks. Electromagnetic waves bend as they pass through ionosphere. Bending depends on the frequency of the signal and the number of electrons along the wave path. Ionosphere can be reconstructed based on the effect that it has on GNSS signals, and this is the basics of GNSS remote sensing. Next slide. Next page, please. Today, observations of permanent GNSS receivers
Which slide, please?
This is right, yes.
This slide, okay.
Today, observations of permanent GNSS stations are one of the most important tools for ionospheric studies. Slant total electron content, or STEC, is defined as the number of free electrons in 1 square meter column along the satellite receiver line of sight, and is estimated with GNSS receivers observations. Actually, this parameter is obtained from linear combinations of GNSS receivers observations. The obtained STECs from satellite geodesy are utilized for single-layer modeling of ionosphere. In single-layer ionosphere modeling, the total number of electrons in 1 square meter column along the zenith direction is going to be modeled. In fact, ionosphere is assumed as a thin layer For example, at altitude of 450 kilometers, which all electrons are concentrated on it. The satellite receiver line of sight intersects this thin layer at a point called ionospheric piercing point, or IPP. Mapping S-TEC to the zenith direction of an IPP results in vertical total electron content, or VTEC. This is done by a mapping function in terms of the zenith angle of line of sight. S-TEC and VTEC are expressed in total electron content unit, or TECU. Each TECU equals to 10 to 16 electrons per square meter. The main purpose of single layer modeling is to express VTEC values in terms of geographic, latitude, longitude, and time. There are two common approaches for the purpose of single layer modeling, function-based and grid-based approaches. Next slide, please. In addition, S-TEC can be used for ionospheric tomography too. Tomography is a reconstruction of the ionospheric electron density, which is the number of electrons per cubic meter. The purpose of ionospheric tomography is to explain electron density in terms of position and time. There are also three common methods for ionospheric tomography: function-based, grid-based, and voxel-based. Voxels are volumetric elements in which the ionospheric characteristics can be assumed to be constant. For example, here we have two ionospheric electron density profiles for day and night obtained from a tomography method. And as can be seen, electron density values during the day are more than night, and electron density increases with altitude and reaches a peak and then decreases. Finally, it can be said, obtain the S-TEC from satellite geodesy and GNSS receivers measurements is a valuable parameter for both ionospheric single layer modeling and ionospheric tomography.
Thank you very much, Dr. Hani Mahboubi from Samarkand University. Thank you very much.
Thanks.
Let's come back to the slide that I have had. The next one is about radio occultation. Is Mr. Hidayati around?
Yes, Professor. Hello.
Hello.
Do you have my voice?
Yes,
How are you?
With you. Nice. Thank you very much. Welcome. So,
Yeah.
you wanted to talk about occultation, and I see that in your slide you have this this animation that I have created. Please go ahead.
Thank you very much. I'm very glad to be in this scientific seminar. In one of the most important use of GNSS remote sensing is GNSS radio occultation technique. If I say it in brief, you see a signal transmitted from a GPS satellite and go through the atmosphere and received by the GPS receiver in a low satellite affected by the troposphere and ionosphere. The effect of ionosphere and troposphere on the signal path could lead us to retrieve some interesting parameters like temperature, pressure, water vapor, humidity, water vapor pressure, and humidity. These techniques works on the calculation of the bending of the signal. If you see in this picture, signal go through the troposphere or ionosphere, it bends, and we could retrieve the parameters like temperature, pressure, and water vapor pressure from the bending angle of the signal. Next slide, please.
Sure.
Thank you. In this picture, we retrieve the refractivity, temperature, and pressure profiles from bending angle calculated from the GNSS radio occultation technique. In this method, there is some benefits when we compare this method to the classic method, meteorological method like radio sound, like measuring directly the pressure, temperature, or water vapor pressure and humidity. We could see the resolution, the high resolution of this technique in this graph simply by calculating and without wasting money, without any instrument, we could retrieve temperature, humidity, pressure, and refractivity at the different layers of the atmosphere. Next slide, please, Doctor.
Yes, please.
In my MSc research, I used the GNSS radio occultation technique to climatology classification. In this method, we use one parameter to classify the climatology changes in the Earth. For example, in my study, I choose the minimum temperature, and based on the minimum temperature, I classified the climatology region of a country of Iran. You see, the result of this study that we have about 10 class of different climatology regions in Iran. And in the right picture, we compare the result of GNSS radio occultation technique with the classic meteorological method to classify the region of Iran. Thank you, Doctor.
Thank you very much, Mr. Hidayat. Just one question: which method for classification did you apply, actually?
We use the K-means.
K-means. Okay.
Yes, we use the K-means to classify. Yes.
Okay. Thank you very much, Dr. Hidayat, for the
Thank you
presentation.
for your time. Thank you.
You're welcome. Let us move on with my presentation. So, well, we have been here as far as I remember. Oh, okay. Let's go to the. That was rather long. So GNSS reflectometry actually is another hot subject, and the idea is that the signals that they are actually, we call it multipath. Multipath is a disturbance actually in positioning when we work with GNSS actually, especially for measurement. But it can be used as a useful signal. For example, there are low orbiters that they are now moving, and they have some specific sensors and antenna to receive the reflection from the Earth's ground. GNSS satellites, they send signals permanently or continuously down to the surface of the Earth, and they are reflected back. So if we can measure the reflection, then we can study the changes. For example, in the beginning, I said that you can use a GNSS reflectometer for determining the soil moisture, because the signal can somehow penetrate a little bit to the surface. Then based on the reflection, that you can estimate this, how much moisture exists in the soil. So that is one thing that actually it's done. Let me see another one here. For example, this is what has been done in Onsala Observatory in Sweden. Actually, they have put two antennas, one in that form, this upward and one downward, and the main issue was to receive the reflection, the reflected GNSS signals back to the antennas. And based on the position that he gave from that one to run the upward one and the downward one, they can measure the sea level changes, because this signal can be reflected from the water surface as well. So that is done actually. There is such a station in Onsala Observatory, and they are working with that. And now the last subject that my studies that I'm studying actually these days. So you know that these days all vehicles moving around the Earth are equipped with GPS GNSS receivers, and they all rely on the satellite signals. But the problem is that there are interferences, unwanted, wanted or unwanted, intentional or unintentional. They can influence the signal. For example, if the aircraft is trust that too much on the GNSS signals and some interference happens, this will be a catastrophe for the crew, people in this aircraft, and people outside, even at the ground. That would be dangerous. So the one issue is that if something happens, some interference happens, how can we detect it? It is called actually the subject localization or geolocalization. So two types of interference normally it happens, and one is the jamming. So it's just that they send another an instrument to jam the signals. It doesn't let the GNSS receiver receive the signal. That was one way. And spoofing is that they falsify the signal. It sends the signal at the same frequency, but with wrong information to the users. Then in that case, there is the risk of hijack of, for example, drones or even those autonomous vehicles. They are working based on the GNSS satellites. So that was what idea that I was that okay, if we have some receivers around this area which can receive this interference signal, so they can detect and receive this signal, we can determine the position of the interference. So here I have done a study for optimizing a network for the Landvetter airports in Sweden. So above, I have used two types of measurement. One is the time of arrival. It means that the time is arrived to the receiver from the unknown source. We don't know from where, but we know the time. And or angle of arrival, where we know the direction, from which direction the interfering signal is coming to the receiver. So I designed it. I selected 3 points. Let me show it on the right-hand side. The most on the right side, you will see 3 places that I have selected over the area, and with some based on some a priori points, as you see here on the figure A. And these are the approximate position of a network, secure network that I consider for that, and I let the coordinates of this point vary inside these boxes or inside this area to see if I can minimize it. What you see here is the DOP, dilution of precision. You see here, this is a very high value here around this point N. And after optimization of the network, and I could improve the DOP for 2 actually. And this value is got a little bit smaller. In the figure B is the optimized network. The points are moving a little bit to the sides. And in both the 2 figures down, you will observe actually the DOP based on the angle of arrival. So as you see that again, the same pattern as you see, and you see in the units of 2, the DOP can be improved actually by can be improved by that. So by a small change around we can improve the quality of the localization. So that is what I am going to do these days, and I have focused on this. I am not going to develop this theory about optimization of the networks and toward wireless systems and indoor navigation. That I am still working on it. So thank you very much. That was all I wanted to present for today. So if you have any question or remark, I will gladly answer or listen.
Yes, thank you, Professor Merti, for this great presentation. And if you If anybody wants to ask question, we can get it. Is there anyone? And maybe I want to say something about this presentation. First of all, thank you. As you know, especially in Turkey, when I find the time, I try to speak to both students and a teacher, and the students almost say that the geodesy is so boring, and then we don't want to study on it. And especially in Turkey, geodesy, not geomatic, geodesy. And remote sensing and the GIS is more popular when they compare to geodesy. But I think that this is reverse for me because I am also a geodesist. And for this presentation, I think that we again saw that the geodesy is a reference source for the many both location-based studies or the other atmospheric reflectometry. You mentioned a lot of things from the GNSS reflectometry, the gravity field, and the atmosphere, and other many studies. And the basic source is the geodesy, and this is unchangeable. I think that.
Well, I would say that I make a joke with my friends normally in my presentation. I say that we are everywhere and nowhere. Everywhere and nowhere. Because, for example, people around, they all use or products without knowing that. You open your mobile, you have a map, navigator in that. You have a navigator in that. Who has get the coordinate? These are the products that we geodesists are behind it, but nobody knows that. GIS people, they use maps.
Yes.
Am I right? They use reference, what's it called, reference systems. They use projections. These are the things that we have done it. We have created these things. We have.
Yes, and I want to express again that thank you, because you showed us again and you remembered us again, and this presentation made us love geodesy again. I think that.
I hope so.
Maybe also should remember we should allow it.
I am happy to hear that. But to tell this remote sensing guys, okay, who will compute the orbit for you?
Yes.
Simple question.
Yes, simple question.
Yes, it's very important. This attitude and these things, these are the things that we geodesists work on that. The orbit of this remote sensing satellites we are behind. We are geodesists behind it. Anything that you mention, I can say, where are we in that? Where we are in that subject. We are everywhere, but nowhere. Nobody sees us. We are hidden. We are hidden. Yes. So something like that. But when they realize it, is when they remove us. Then we realize that the problem will come. Yeah. As long as we are there, nobody cares. But when we leave, then it is. But I would say that geodesy is a engineering subject with the background in geometry. Geometry is the first thing came to human eye before physics and this thing. Go to very past. Geometry is the beautiful thing with geometry is that you can communicate with nature directly with your eyes and with mathematics. Geometry is something that connects your reality with mathematics. So if you learn this, then you will understand what is geodesy. When you say geodesy, I say it is geometry. Yes. Not when you say geodesy to people immediately look at the earth. Why? But when I say that geometry, everybody will think about mathematics. Yeah. But you have geometry and geodesy. So geodesy It's the same thing with geometry, but we apply it in engineering for a specific purpose, for studying the shape and size of the Earth.
Yes.
This is, well, this was what I have in mind to explain a little bit about my journey in geodesy. It was not it's very general. It was what I have observed. If you observe something else and some other application, that's fine. Let me know that. I have no problem with that.
I asked this question deliberately because I also wondered your comments about the subject. As you said, first the people hear the geodesy. Yes, the people looks to Earth, but in fact, our daily lives, yeah, is around the geodesy. And
Yeah.
it is nice to hear the same thoughts from you. It is nice for me, and today is the very good day for me because the other country and your student and the Dr. Andenet, had Dr. Edayeti, Dr. Hani Mahbubi also participated in this meeting and talked about his studies, and that's also very well for me. And I also thank uh, them, all of them, and maybe you can also say the last word. Maybe you want to mention.
So I'm also very thankful to you, Samad, with the idea of doing this online seminar, and I'm really honored for your invitation. I really enjoyed actually being with you all. Also, I am thankful to the guys who assisted me during the presentation, Dr. Hani Mahbubi, Dr. Hedayati, Dr. Andenet 1, Andenet 2, Andenet Negocia, Andenet
Evet.
Xavier. Thank you very much for assisting me and participating in my presentation. I'm proud of you all. Thank you. So, if you have any comments or remarks, so I gladly listen. Otherwise, I wish you all good luck.
Thank you for your good wishes. Maybe we can meet again in near future again if you have a time. Maybe we can do again maybe different, more deep. Maybe you can also speak to another deep talks.
Okay.
Maybe, well,
It
I don't
will be
know.
very expensive for you then. Deeper, more expensive. Just kidding. No, we are all scientists, we are all teachers, and we love to give information. That's no problem. As long as my time allows, I am with, no problem. So no
Thank
problem.
you.
It was a joke, don't worry.
Thank you. And I also thank all participants to this meeting. And I hope that, yeah, maybe I can say bye-bye. By the way, this meeting will be shared by the chat section. Yeah, because we will save it. We saved it. And
Yeah, please, if you